Hello everyone, I'm Nia Shahzami, a computer engineering student at Firdaus University of Mashhad. I have prepared this project for the Electrical and Electronic Circuits course under the supervision of Professor Dr. Sadouri. The topic of my project is AC analysis of electronic circuits using Ngspice with a practical study of Ngspice. The main goal of this project was to go beyond textbook theories and learn how to actually analyze a circuit from a frequency perspective in 30 volts. In this video, I intend to show all the steps completely practically and step by step, from software installation to interpreting results. Okay, so to begin with, let's see why we actually need AC analysis. When we design an electronic circuit, for example an amplifier or a filter, we cannot rely only on DC analysis or transit analysis. And why? Because in the real world, signals have different frequencies, and our circuit responds differently to each frequency. For example, suppose you have designed an audio amplifier. This amplifier should properly amplify signals from 20 Hz to 20 kHz, which is the human hearing range. But how do you know that your circuit works uniformly across this entire range? This is where AC analysis comes to help us. With AC analysis, we can see the frequency response of the circuit, draw body plots that show how the circuit behaves, examine the phase of the output signal relative to the input, and in circuits with feedback, check the stability of the system. To do this work, I used Ngspice. Ngspice is an open source and free simulator built based on classic Spice. This tool is widely used in industry and has the same power as commercial simulators. Next is to prepare the work environment. To do this, you can refer to the document of this project. You can see all the steps from Ngspice installation to VS Code installation and how to execute your Ngspice netlist in VS Code. Assuming we have already done this, let's understand how to create a netlist for AC analysis in Ngspice. In Ngspice, every component starts with a specific letter. R for resistors, C for capacitors, L for inductors, V and I for voltage and current sources. Here's the critical part. You must have at least one AC source in your circuit, or the analysis will be meaningless. Let me show you a simple RC low-pass filter example. As you can see here, here's the netlist. Notice the AC source definition, which is V110AC12. This creates a voltage source between node 1 and ground with an AC amplitude of 12 volts. Other resistors, R1 connects node 1 to node 2 with 30 kiloohms, and capacitor C1 connects node 2 to ground with 100 microfarads. The AC command specifies our analysis, and we will dive deeper into the next part. The AC command is your gateway to frequency analysis. The general format is AC, one sweep option, points, a start frequency, and a stop frequency. We have 3 sweep options. First is decade sweep, octave sweep, and then linear sweep. Let's start with decade sweep, which is specified by DEC and is the most common for body plots. It distributes points logarithmically. For example, 10 points per decade means 10 examples between 1 Hz and 10 Hz, another 10 between 10 Hz and 100 Hz, and so on. And as we can see in the example in here, this gives us 10 points per decade from 1 Hz to 1 megahertz. Next is octave sweep. It's less common but useful when you want points at frequency doublings. Each octave represents a 2x frequency increase. And the final one is linear sweep, which is specified by LIN. Points are evenly spaced across the frequency range. This is great for narrow frequency bands but inefficient for wide ranges. And as you can see in this example, this gives us exactly 10 evenly spaced points from the start frequency to the stop frequency. And the important constraint is that the start frequency cannot be 0 in logarithmic sweeps. It always starts from at least 1 Hz or higher. Okay, the next part is to choose the right frequency range. Choosing your frequency range correctly is crucial. Here are the key principles. First, the start frequency. Begin at least 1 decade below your critical frequencies. For a filter with 160 Hz cutoff, starting at 10 Hz captures the flat response region. The second one is stop frequency. Extend several decades beyond your critical frequency to see the full roll-off. For that same 160 Hz filter, going up to 10 kHz or even 100 kHz shows the complete curve. The third condition is avoid narrow ranges. Don't just sweep around your cutoff frequency. You'll miss the big picture. And here, let's see this in practice with our RC filter. As you can see the netlist in here, this is the visual body plot for the visual resulting body plot. The theoretical cutoff frequency is 159 Hz. Our sweep from 1 Hz to 100 kHz captures the flat passband below 100 Hz, the transition around 160 Hz, and the minus 20 decade roll-off extending to high frequencies. This complete picture is essential for understanding your circuit's behavior. Okay, the next part is visualizing the results. Ngspice provides special functions for AC analysis. Which are VDB, which is voltage in decibels, VP, which is phase in radians, and VM, which is voltage magnitude. Here's how to plot gain and phase, which you can see the netlist, the Ngspice netlist in here, and this is the resulting 2-panel body plots. And yes, you can see it here. The magnitude plot, which is on the top, has y-axis, which specifies the gain in decibel, and the x-axis, which is the frequency. And it shows how signal amplitude changes with frequency. The next one, the phase plot, the bottom one, has the y-axis as phase in degrees or radians, and x-axis in frequency, which shows the time delay between input and output. For our low-pass filter at low frequencies, gain is 0 decibel, and phase is also near 0. And at cutoff, which is 59 Hz, gain drops by 3 decibel, and phase is near minus 45 degrees. At high frequencies, gain continues dropping at minus 20 decibel, and phase approaches minus 90 degrees. Okay, the next part is extracting gain, phase, and stability margins. For stability analysis, we need 2 critical measurements. The first one is phase margin. The difference between your circuit's phase at unity gain and minus 180 degrees. You want at least 45 degrees for good stability and fast response without much delay. The second one is gain margin. How much additional gain you can add before the circuit becomes unstable at the frequency where phase crosses minus 180 degrees. Use this command, which is .meac command, to extract this automatically, and you can see the code in here. For a common emitter amplifier example, you can, as you can see the netlist in here, this is the resulting body plot with margin annotations. If at the gain crossover frequency where gain is 0 decibel, your phase is near minus 135 degrees, then phase margin is 180 degrees minus 135 degrees, which results in 45 degrees, which tells us that it's stable. If at the phase crossover minus 180 degrees, your gain is minus 1 decibel, then gain margin it will be 9 decibel, which is also good stability. Both positive margins mean your closed loop circuit is stable. And the next part is introduction to Ngspice. Let's briefly look at Ngspice, which is a Python wrapper for Ngspice that enables automation and advanced data processing. Here's the same RC filter in Ngspice, in which you can see the code in here. And extracting the results is quite simple, and you can also see the Python code in here again. And this shows the body plot output. Ngspice has some advantages, for example, scriptable and automatable, direct integration with NumPy or Pandas, and perfect for parameter sweeps and Monte Carlo analysis, and results immediately available as arrays. It also has some limitations. For example, requires Python environment setup, no graphical schematic editor, and it still depends on Ngspice backend. You may ask when we should use Ngspice. We should use Ngspice when we need automation, batch processing, or integration with data science workflows. And we use Ngspice CLI for quick one-off simulations or when you prefer working directly with netlists. Now for the final part, let's recap what we have covered. At first, we learned how to build a proper netlist with AC sources, understanding different types of sweeps. In the continuation, we learned how to choose appropriate frequency ranges, plotting and interpreting body diagrams, extracting gain, phase, and stability margins, and finally automating with Ngspice. The key takeaways were always include an AC source with non-zero amplitude, use DK2 for most body plots, extend your frequency range beyond critical points, use VDB and VP for proper gain and phase plots, and also check stability margins in feedback circuits. And also, as we have learned, AC analysis is fundamental to circuit design. Master these techniques and you'll be able to analyze filters, amplifiers, and control systems with confidence. Thanks for watching and happy simulating.